Hello physics class, this is Armand Ramazani, and I'm going to do a demonstration for problem number 7 of chapter 4 in the physics textbook. So the problem reads, what if acceleration is not constant? A particle starts from the origin with velocity 5 hat meters per second at t equals 0 and moves in the xy plane with a varying acceleration given by acceleration equals 6 times root t j hat meters per second squared, where t is in seconds. Determine the vector velocity of the particle as a function of time. Determine the position of the particle as a function of time. Okay, so let's write out the givens first. So we know that the v naught, or the initial velocity, is equal to 5 I hat meters per second. And then the acceleration is equal to 6 times root t meters per second squared. Okay, so what we have to do is that we have to use antiderivatives in order to figure out the vector velocity and the position as a function of time. So we start with the acceleration, and acceleration is a derivative of velocity. So we know that the acceleration is equal to 6 times root t j hat, which means that it's in the y direction. So what we have to do is that we have to change the square root into an exponent. So it'd be 6 times t to the 1/2 power. The 1/2 j. So if we want to find velocity, we have to find the antiderivative of the acceleration. So what we would do is we have the velocity vector is equal to, we're going to put 6, and then if you remember, for derivatives, what you would do is you would do whatever the exponent is and minus 1. So if we're going to do the antiderivative, we're going to add 1. 6 times 3/2. Okay? But we can't, because if we were going to go in the reverse direction, if we were going to take the derivative of the velocity, it wouldn't become 6t to the 1/2 power. So we have to multiply it by the reciprocal of whatever the power is, which is 2/3. So if we were to take the derivative of that and multiply the front by 3/2, then it would become 6 times root 2. But we have to add in a constant, because when we take a derivative of a constant, it becomes 0. So we just have to put that placeholder. And in this case, that placeholder constant is v naught, which is the initial velocity. So we can simplify it, and that's a j hat direction. So the velocity initial is 5 I hat meters per second, and and then the other component would be 4 t to the 3/2 power j. But you would be adding it since it's the I hat and j hat, or to put it into a vector, you could say 5 comma 4 t, oh excuse me, just 5 4t to the 3/2. Okay, now that is the velocity of it. Now we have to find the position. So what we have to do is we have to take the antiderivative again. So I'm going to move it back up here. So in order to take the antiderivative again, of a constant, you would just add t, because then what you would do is, so r for the position is equal to 5t I hat, because the derivative of 5t is 5. And then we add it to, I'm going to leave a little bit of space, 4t, and then it's going to be to the 5/2 power. So then we'd have to multiply it by 2/2 in order to counteract it once we take the, if we were to take the derivative, plus a constant, which in this case would be x naught, or the initial position. But here it says that it's the position, the particle starts at the origin, which means the x naught is 0. So we see that the position vector is equal to 5t I hat plus 8/5 t to the j hat, excuse me, 5 has the j hat. Okay, so this is the answer to B. And this is the answer to A. Okay, thank you very much, and thank you for watching.